another remark, I would like to define this curve actually. So have you seen this notion of curve? Curve, how you compute the curve. So you have curve, gradient and divergence actually. Okay, so the divergence is the del, the dot product of the del with the E actually. And curve,
Cross product. Cross product with
cross product of the divergence and E actually. But why the curve is like that actually? So that's it. Let's think about it. So I know that if f is irrotational, then this must be true. Okay, so partial fi by partial xj is partial fj by partial xi, right?
Yes.
This must be true. And maybe let's think about the dimension 3 actually specifically. Okay. Let's think about the dimension 3. Okay. So what does this also mean? That their difference is 0. Okay. So this means that these differences are 0 actually. Okay. These three differences are 0. And let's think about the kernel of the vector field F now. Okay. So what is physically kernel is doing? So you have a vector field which is defined all over the domain, and you want to know that if you give me a specific point within that domain where say field is defined, what is the amount of the rotation that is happening, at that point or in the neighborhood of that point actually. Okay. So the curl is that the measure of the rotation of a vector field. And I gave one example that sometimes the vector fields that are in your opinion, the flows that you see that they are going fine, but still you can find curve in the vector. Okay. What could be the other examples? Getting into it, we have learned about it already. So what would be the curve actually? So I know that I can compute this curve by taking the dot product of del and f, or cross product also. If I have ijk, partial by partial x, and partial by partial y, and partial by partial z. Okay? And I have f1, f2, and f3. So this is going to be what? So the first component is going to be partial f2 by partial x minus partial f1 by partial y, and partial x by partial f3 minus partial f1 by partial z. But if you multiply it with the minus, you're going to have partial f1 by partial z minus partial f3 by partial x, and what? The third one. Okay, so I did a silly mistake. So if I get rid of this, I'm going to have f3 and y, okay, and f2 and z, okay. And the final is going to be this guy. Okay, you have this partial f2 by partial x and partial f1 by. Now think about it. Think about it. Now, if f is irrotational, I know these guys are 0. These guys are 0. And if this is 0, what is this? Okay, so you can have in three-dimensional, a vector field is irrotational if and only if del cross f is 0. Okay, but in 3 dimensions, not in higher dimension, not in lower dimension, but in 3 dimensions. In higher dimension, you only have a way to verify the conditions actually. Okay. Because you can already see that. Can I define curve in 2 dimensions? Think about it. So what would be the meaning of curve in 2 imagine you have this 2 by 2 determinant actually. Okay. Can I compute it?
No, sir. No, sir.
So curl in this form only makes sense in 3 dimension actually. Okay. But if you want the irrotationality, you have these conditions which can help you. Okay. Good.
So by this definition, can we drive the irrotationally with respect to linear lines?
Irrotationality of linear lines. Okay. I mean, obviously, what do you mean by if a vector field is kind of a uniformly moving actually? So it simply means that the vector field is kind of depending on the polynomials. Either polynomials, linear polynomials are constants actually. The components are constants, and obviously is going to satisfy the condition.
An example of water, the rotation was caused because of difference of velocity.
Yes. Because so in a canal or maybe a river, for example, that is going on right near us actually, you can see that you will see more flow in the middle, and it's not a uniform flow actually. It's a bit turbulent flow. Now, you can, in 3 dimension, you can write Poincare Lemma in another version. So what would be the version of a 3-dimensional Poincare Lemma actually? So one version is this. What would be the other version? So you can say in 3 dimension that if the curl of f is 0, so if your field is irrotational actually, okay, and f is defined on, okay, f is defined on what? On a convex set, obviously in R3, then f is gradient. Simple. In other words, to know in 3 dimension whether a field is a gradient of a some scalar field or not, just check that whether it's whether it's curl is 0 or not. But yes, obviously this is an important condition to do that. You need to have the convexity. But if you take up, for example, a vector field that is defined on the entire, for example, R3, then you just have to check this condition. Okay, because the entire R3 is convex. Okay. So this could also mean that then you can find the potential of the f. So if it is irrotational, then you can find the potential. So another version of Poincare Lemma could be that imagine you have a vector field for which the divergence of f is 0. It's not diverging out actually. For example, like the magnetic field. The magnetic field is a divergence free kind of a vector field. Why? Because think about it, if you have a magnet, okay, and you break it, so it is going to contain south pole and north pole actually. Okay? So if you break it, okay, so automatically a new pole will be created actually. Okay? So it's not like, so in other words, the magnetic field of lines want to stay within the pole. They don't want to spread actually. I mean, if you've seen this, north to south, the lines goes from north to south to south to north. Maybe north to south, something like that. Okay. So you might have seen this picture, huh? Okay. Something like that. you have this field, okay, you can define these are, lines of the forces actually, okay, but it's not spreading, okay, it just don't want, so it want to stick to the, the magnet, it doesn't want to, what do you call, a spread, okay. For example, if you have, if you, so in the middle of a lawn, if you put a water source actually, and you see this flow want to spread actually, okay. So it's not a, divergence free field actually. So it contains the divergence. You see the light actually. Okay. It's not necessarily so it just spreads. So you have the source of light and just want to spread all over actually. Heat want to spread all over actually. So these are not divergence free fields actually. Okay. So what we are talking about? We are talking about the divergence free field. Okay. So there is a specific name for it. Field, such fields. These are called solenoidal field. I think yes, solenoidal fields actually, something like that. I mean, I could be wrong on the spelling, but yes. So if you have a solenoidal field, then you can do something interesting. And that interesting thing is that you can find another field G that is, whose curl is this up? Whose curl is this up? Okay. So in other words, if the divergence, so if I have a vector field F that is divergence free, then it must be the curl of some other vector field actually. Okay. And in magnetic example, you can really see the curl actually. You can see that the field lines or the magnetic, lines of the forces are, they want to curl. Okay, they want to curl all around the magnets and within the poles of the magnet actually. Okay, so that's another version of a Poincare Lemma, but in 3 dimensions, obviously. Okay, so let's quickly do an example over it. So let's take a field F, x, y, z, and it's defined in say y, z, cleverly defined x, z, and x bar. Okay? So what must be the divergence of F? Differentiate first with respect to x, 0, with respect to y, 0, with respect to z, 0. Simple. So it's a divergence free field actually. Question, can I compute a vector potential for it? So it's not a scalar potential, this time it's a vector potential actually for F. So in previous case maybe you saw that F can be written as a gradient of a scalar field. Now you are saying that if it is divergence free, you can write it as a, it is going to be basically rotation of something. Okay? In other words, wherever you see something is divergence free, you must going to observe the rotation. It's going to be something that, it's the rotation of some other vector field actually. So the question is, can I find G? So how can I find G? So what should I do? It should be easy. So I know the components of this vector and just equate them with the components of this vector actually. F is the vector field, so it contains components. What is F1, F2, F3. And del cross G also has components. So we just wrote basically, some components. For example, so YZ would be equal to what? What was the first component in the curve? So it was partial, for example, you may assume that G contains 3 components, G1, G2 and G3. So was that partial G2 by partial Z minus partial G3 by partial Y. right? See the expression we just wrote for the curve. नहीं,
So
पहले
partial
वाला
G3 or
G3 minus G1.
G3 by G3 by Gy
yes
और F2 से
or G2 by G0, right?
लिखा हुआ है.
किधर लिखा हुआ है? Okay, so you can have it. Alright, so what would be the next expression? So xz is partial, so I'm getting rid of the middle term, so it's gonna be,
G1 with respect to Z,
so G1 with respect to Z minus
derivative of
G3 with respect to x actually, okay? And the third is going to be xy, so it's gonna be G1 with respect to y minus
G2 with respect
Sorry,
to
G2 with respect to x
X. Yes.
and
G1 with
with
respect
respect to y. Okay, so this is the, so you got these three Slee equations actually. Okay, so if you want to compute a vector potential for it, okay, so you'll find this way a bit sillier actually. How it's going on and what's going on, but you know, it's not that silly. Okay, so here's the thing. I want to say that difference of these three things should be yz. So how can I have a difference of these two things to be yz? So one way could be that you say that partial g3 by partial y is this yz and partial g2 by partial z is 0. So that's one way to do it. Okay? And I will say that no matter what way you take, you're always going to reach to the same g actually. So g would not change actually. Okay? G would not change, we'll see. So their differences satisfy this condition. So what can I say about the G2? So it's going to be a function of x and y actually, equal to a constant. Right? G2 is going to be a function of x and y, right? Right? And G3 is going to be simply y square 0 over 2. Okay? Y square 0 over 2. I mean, if you wish, you can add a function of x and z, but you will see that it's of no use because all these will be combined afterwards. And okay, so I mean, just involve one of, for example, take one of the component and just involve one kind of a, for example, a function at a time actually. Okay? So if you are talking about x and y, just involve it, and there is no need to involve or write the constant equivalent of a constant term here actually. You don't need to do it. Okay? But if you wish, you can add it. You will see it makes no difference. Okay? So I got a third component G3, so I need to figure out G2. So how can I do it? So I can play the same game here. Okay? So take partial G1 by partial Z to be xz, okay, and partial G3 by partial x to be 0. Right? So the G3 is going to be what? Is going to be a function of y and z, and I know it already. So this G3 is known to me, so it's not any new information added into it actually. What would be this G1? So I can treat this as that this is going to be x z square by the second component. Okay? How about the third one? So I can guess actually that the G2 by the similar trick you can get to be the xy square upon 2. xy square upon 2. Okay. And so what would be your g? So your g is going to be an interesting quantity, so you need to carefully write it. Because we have ignored a lot of constants actually, the functions that were depending on different things. So, right.
So in G2 we are derivating with respect to x.
Uh-huh.
So we need to integrate with respect to x. So this is gonna be x square times y over 2, I think.
अच्छा ठीक है, x square y over 2, ठीक है. So then my g is x square y over 2. So this guy is xz square. G1 is xz square over 2, and G2 is x square y over 2, and G3 is x
Y square.
y square z over 2 actually. Now I know there will be functions coming out of all three because we are doing integration. So I'm putting them, these all functions as x, y, z. So I'm combining them and putting them as all functions as x, y, z. But you will see that this phi is not going to be phi, it's going to be only, so it's going to be the gradient of the phi. Why it's going to be the gradient of the phi? It's going to be the gradient of the phi because if you're going to take the curl of this g with g plus del phi, then this del cross del phi will become 0. So it will go away actually. It will go away and you're going to have the g. ठीक है? पूरी समझ आ रही है बात? So just go through it. So it's a bit trickier, but it's just really a counterpart of it. So if the curl is 0, you can find a scalar potential, and if the divergence is 0, you can find a vector potential. That's what Poincare Lemma is saying. So it's the end of the chapter. Okay. We will maybe cover one thing more of the chapter, maybe harmonic equations and so on. Okay, it's the end of the chapter. Okay. There are many things in the chapters. Okay. जो कि हम कर सकते हैं.